Alright, hello, Year 12, Extension 1. Oh, no, that's not the right start. Oh well, I'll edit that bit out. Hello, anonymous viewers. I am presenting on Volumes of Solids of Revolution, as you can see. And let's just get right to it. So what we're going to do, we're going to look at the location in the syllabus, some HSC assessment, misconceptions that students will have. We'll have the little teaching demonstration we all know and we all love, and we'll have a bit of justification of that teaching episode at the end. So first up, location in the syllabus. Now, it used to be the old syllabus on the left. It used to be in 2 unit and extension 2, and in 2 unit they would do cone spheres and simple curves over both the x and y axes. And extension 2, they went into dividing solids into a number of slices or shells, and this would lead into the foundational formula of our volumes of solids, which was also taught in unit 2, or in 2 unit if people wanted to, but that's up to them. And then extension 1, it moved into extension 1, so the extension 2 content got completely destroyed. That's out. And then the 2 unit stuff got a bit harder. Now we still do single curves, calculating volumes and sketching. We also do regions between 2 curves and over both the x and y axes. So it's basically the 2 unit stuff just moved into extension 1. Alright, so the skills and why it's important. It's plenty of integration practice, so it ties in there. We're still using graphs. And we can even move into 3D graphs now, which is why our 3D thinking is very important in our volumes of solids. And obviously volumes. So all of this ties in all over the syllabus into this one topic. Now if we look at HSC assessment, so we come around and we've only had 2 years of the current syllabus, but that's okay. We've had 2 different questions. This 2021 one is the region between 2 curves, and so we're creating solids and minusing one solid from another one. And this is very similar in 2020, only now we're talking about trig graphs as well, so sine of x and cosine of 2x. So this is, one of them was around the x-axis, and this one's around the x-axis, and the other one was around the y-axis. And so they're mixing it up a bit, and that's the same throughout the last few years of HSC as well in the 2 unit exams too. And so now we're going to look at some misconceptions. And a lot of students have a very structural misconception to start with, right? There's a failure to grasp the basic principles or relationships, so there's something going wrong that they don't quite understand, and so this leads into many errors along the way. And then they have a lot of trouble manipulating the algebraic expressions as well, so converting forms or just tying it all together in their algebraic work is some problems. And so this is backed up by the HSC feedback, which tells us that students commonly get the wrong order when subtracting the larger solid from the smaller solid. They forget to square the inside of the integration. They're not really understanding the intuitive answers, so they're getting things like volume equals 0 and not really understanding that's not appropriate. They're also omitting pi. So they're getting the equation wrong and they're not really checking their answers. And then backed by the literature as well, so converting forms of expression, that algebraic problem, and determining functions and misunderstanding of the solid formed. So really not understanding what's actually happening during the integration. Alright, I'm going to go into my little teaching demonstration, so I hope you enjoy. I would put my teaching hat on, but sadly I haven't received that yet. Maybe Stuart will give me one. Alright, hello Year 12 Extension 1 and other anonymous viewers watching this video. We're going to do volumes of solids of revolution. And so I think let's get right into it. So we're going to look at what is it, how do we do it, some questions that we're going to cover together, I just dropped my pen, and a recap. Got my pen back, we're good. So what is it? So the Cambridge textbook describes it as a region in the coordinate plane rotated about the x-axis or y-axis. So we're taking some area and rotating it around one of the axes. And so I'm just going to play a small tidbit of this video, and you see this formula, y equals square root of x, going around the x-axis, creating a solid. And then I'm also going to move on to this section, which is now y equals x cubed, but around the y-axis, right? So we can still have volumes around either region. And so I'm not going to watch any more of that. It's pretty much all the same. Alright, so continuing on, because I made a mistake. And so how do we do it? Right, so the formula is the same, pretty much between them, but different. So I've got the examples from the video here, so one on the x-axis and one on the y-axis. And if we look at the x-axis formula, we've got v equals pi between the limits of a and b of y squared dx. And so a and b obviously are limits of integration. You did those in your integration areas as well, and this is very similar. If you look at the formula, you also have that pi y squared dx could be very similar to the volume of a cylinder, pi r squared height. Right? And this is no coincidence. We can actually break down our integration into small cylinders and create the formula of integration that way. So when you do think of integration in terms of volumes of spheres, volumes of solids of revolution, you can think of that formula. Do you have pi, a letter squared, so y squared or x squared, one of our functions, and then dx or dy in terms of our very small height or width, right? And so we're going to go into a few questions on how to do that, and so let's go right into it. So for our questions, I'm going to run into another whiteboard, so I'll pull that open. And so the first one we're going to look at, let me zoom in here so you can see it a bit better, is to find the volume of the solid generated by rotating y equals 2, so that straight red line, about the x-axis, bounded by the y-axis and x equals 3. So if we break this down, let's have a look at our bounds. So we've got bounded by the y-axis. Let's just look at our region first. So I'm only going to draw it up to y equals 2, but obviously the y-axis goes further. And x equals 3. So I'm going to pull this up as well at x equals 3. Actually, you know what? I'm going to zoom in slightly more. Those numbers are quite small. Alright, so we're looking at this region, this rectangular region, which I'm sure many of you could give me the area for, but we're not really considering the area at the moment. We want to learn about the volume. And so we're going to take this, and our revolution is literally revolving this around the x-axis, right? So we're going up and around to create a cylinder around the whole way. Right? We're going to bring that the whole way around. And so to apply our formula, I'm going to change to orange here for our writing. We know that about the x-axis, our formula was the volume. Let me change my microphone here so I'm actually speaking into it. Our volume is equal to pi between the limits of a and b. So in this case, I'll write out the formula first. A and b. Now it's in terms of x because we're going around the x-axis, so I know that I have dx, which means that our formula must be y squared. So pi between the limits of a and b, y squared dx. Now if we continue this, I know that's pi between the limits of 0 and 3, right? Because our x limit is 0 and 3, those orange dots. Now y squared, so y squared, remember this, I'm going to go switch back to blue. As a little aside, I know my function is y equals 2, and so I know my y squared function is 4. Right, so I'm going to write that in as y squared, so 2, because y equals 2 squared, and you could just put 4 in here straight away too, dx. Right, so then we go away and we solve this. I know all of you are very confident in solving this. We're going to get 4, and then we get pi, and we're going to integrate that, so 4x between 3 and 0. Now you can take the constant out. In this case it doesn't quite change. So we're going to get pi outside of 12 minus 0, and our final answer will be 12 pi for the volume of this revolution. Right? And so now I think I spoiled it a little bit before, but we're going to look at what solid is actually created and how can we verify its volume? How do we know we're right? And so if we revolve this, I'm actually going to pull up a little simulator here for you guys to see. Now this in GeoGebra is pretty much what we already did. We've got our y equals 2 and our limits. And so if we were just looking at the x and y axis, and we revolve this, this is what we would see. We would see just a red thing coming around, right, forward and back. I'm going to change the view a bit. Might be a bit trippy for you. And now we're going to watch it again, and so you can actually see it going around and making a cylinder, right? And well, we know the volume of a cylinder, don't we? Right? Volume equals pi r squared h is the area of a circle times by the height. So I'm going to come back here, and then we're going to talk about what solid is created, so we know that's a cylinder, and how can we verify its volume. So actually, if I pull back up here, we know that in our cylinder, let's change to a different color, let's change to green. Our cylinder here, essentially that circle is a cross section of our cylinder. I know the radius of my cylinder is just the y value, so I know the radius of my cylinder is 2, and the height is the length of my cylinder, right? So in this case it goes all the way up to x equals 3, so my height is 3. So if I simply do v equals pi r squared h, right, I'm doing pi times 2 squared times 3, which I know is 12 pi. Right, which is the exact same thing. So we know we're correct when we do this. So that's really nice. I think one special thing about volumes of revolution, and we're going to bring it across here a little bit, is can we come up with a general formula for this solid? So for the cylinder, can we actually come up with the formula by doing this? And I'm going to bring this question across now so we can look at the diagram all at once. I'm going to bring it all the way to the other side. All right, here we go. And now, if we wanted a general formula, we have to generalize everything, right? So we have a cylinder with a radius of 2, but that radius really could have been anything, right? So what if I said in my working that I want my radius to be r, it's any radius. So I can say y equals r, because in this case y is our radius. And for my height, well, I know that the height of my cylinder, to generalize it, is just going to be h. It could have been 2, 3, 4, could have been 17.3, right? So I'm just going to say that my height here, my bounds is going from x equals 0 to whatever the height of my cylinder is, x equals h, right? So that's my bounds. Right, everything else in this question stays the same, and so we're going to work through this again, and I'll go through this a little fast. AB, we're going to have the same formula, y squared dx. So we've got pi r squared h, right, in terms of our knowing our formulas right. Now in this case, y equals r. So if y equals r, I know that y squared equals r squared. So I'm going to substitute that straight in. Pi, my limits are from 0 to h of r squared dx. And now I'm going to solve this again, so pi, and then we're integrating in terms of x, so r is essentially a constant, so we get r squared x between h and 0. We get pi outside of r squared h minus r squared times 0. And if we expand all that out, we get pi r squared h. Ah, cool! A full cylinder. Alright, so we've just constructed the formula for that cylinder, which I think is really amazing. Now I'd like to challenge anyone watching, can you come up with a formula for any other spherical, well, yeah, any other solids? If you want easy ones, well, easy, right, try a sphere or a cone. I can't think of any others off the top of my head, but those two. If anyone gives them a red hot go, I'll give them a high five in class. And if you get them both, I'll give a high 10. Alright, so that comes to the end of the questions. We'll expand on this more, and we've only done the x-axis here, but we can do the same thing around the y-axis, and that'll happen in future lessons as well. So we've got a bit of a recap. So we know that the formula is the same, but different. Now about the x-axis, right, we know that the volume equals pi between the limits of a and b of y squared dx. Right, remember pi r squared h. Right, we are essentially cutting this into tiny cylinders. And the y-axis is almost the same, except we're doing it in terms of the y-axis. So we can always think of in terms of what will be the dx, right? So if it's over the x-axis, it's dx. If it's over the y-axis, it's dy. And then everything else works out. Do not forget the square. You will not believe how many students forget the square and how many do not remember to put the pi in. And if any of you don't do it, I'll be crying in my bed. But I don't think any of you will. I think you're all good students. Thank you very much. If you have any questions, post them on wherever this video is posted. For all of you anonymous viewers, I'm sure it's on the discussion board. And I'll see everyone for the next lesson. Alright, so teacher hat comes off, imagine it. I'm sure you have great imaginations. Justification, so in terms of why I presented my teaching lesson this way. Now, this is something usually presented in 2D, and I think having these simulations and actually presenting it in 3D really brings together what the students are actually creating. They're actually creating 3D volumes. We're uncovering foundational formulas, so they're being able to look at where do all these formulas that I've been using since grade 4 actually come from. And so I think that's really fun, really, and really gains student interest. And we get mathematical exploration, so we really want our students to actually explore mathematics. They want to enjoy it, not just remember facts. And I think becoming an explorer is really one of the greatest ways of finding something interesting. And that brings us to the end of it. So thank you very much. Next lesson, I'll do a series of these, rotation about the y-axis. I'm not actually going to do a series of these, but for anyone that wants it, I'll catch you there. Here's some references, a bit over time, but don't kill me, it's fine. Alright, enjoy, bye!